welcome to this video. So today we will learn how to solve the very famous stochastic differential equation, the Ornstein Uhlenbeck SDE. The SDE is written in this form: dxt equal to theta times mu minus xt dt plus sigma dwt. So let's first review the general concept of stochastic differential equations. Basically, stochastic differential equations, or SDE in short, model systems with random influences. It has this general form: dxt equal to bxt t dt plus sigma xt t dwt. So here b and sigma are functions of x and t. And wt is a Wiener process, or you can call it a Brownian motion. Then we can have a special case, which is the Ornstein Uhlenbeck process. This is an important SDE in physics, finance, and other fields. It actually models the mean reverting process. So the SDE we have seen, it takes this form: dxt equal to theta mu minus xt dt plus sigma dwt. So here theta positive is the rate of mean reversion, and mu can be interpreted as the long-term mean, and the sigma is the volatility parameter. So next, let's see how we can solve this SDE. So step 1. So first, let's consider applying the integrating factor exponential theta t to xt. So we are going to calculate the differential of exponential theta t times xt. So by the product rule of Ito formula, so we have that actually this is equal to the differential of exponential theta t times xt, and then plus exponential theta t dxt. So for the first term, the differential of exponential theta t by taking the derivative of this function with respect to t, so we have that this is theta exponential theta t, then we include xt dt here. Okay, so dt corresponds to this differential. And for the second term, we copy it here, and for this dxt, we can copy the SDE in. Okay, so it is equal to this quantity. So now we have this summation for this differential, and we can see that so this term actually cancels with this term, because you have a theta here, you have exponential theta t here, you have a xt here dt. So, and also for this, the term in the second part, so we have exponential theta t, theta xt dt. So these two term cancels. So the remain would be theta times mu times exponential theta t dt plus sigma exponential theta t dwt. So now the right hand side does not involve any xt. Okay, so we go to the next step. We integrate both sides from 0 to t. So for the left hand side, we would have that the ending point exponential theta t xt minus the initial point x0. Actually, it should be exponential theta times 0, but this is always equal to 1, so we don't include this one factor here. For the right hand side, we have two integrals. The first integral is theta mu times the integral of exponential theta s ds integrated from 0 to t. And the second integral is actually sigma times the integral of exponential theta s dws from 0 to t. So the first integral has a closed form formula, so which is just corresponds to this quantity. Okay, so exponential theta t minus 1 divided by theta, but this theta cancels with this. Okay, so theta times this integral would be equal to this term. Okay, and we copy this mu here. And for the second integral, we just remain in here. Okay, and we move this x0 to the right side, so we have that a formula of exponential theta t xt. Again, on the right side we don't have xt, so we are very close to get the closed form formula. And then we move this exponential factor to the right side, so we get that. So xt is equal to exponential minus theta t x0 plus mu times 1 minus exponential minus theta t plus sigma exponential minus theta t times this integral with respect to this Brownian motion. Okay, so we can reorganize these terms, actually the first two terms, and put this mu here and combine these two terms involving exponential minus theta t. So we have exponential minus theta t x0 minus mu here. From this solution, so we can see several important properties of the solution. First of all, for the first two terms, it is deterministic, right? And the only random part of xt is the last part, which is an integral with respect to the increment of the Brownian motion. And we know that the increments of Brownian motion are always normally disputed. So this integration is always normally disputed. And we can somehow calculate its expected value. The expected value of xt is basically the first two parts, because the expectation of this integral, which is basically the integral of the Brownian motion increment, would be always equal to 0. So the expectation of xt is these two parts. So, and also we can calculate the variance. So basically the variance of xt is contributed by the integral. Okay, so is this part, right? So it would be sigma square exponential minus 2 theta t times the integral of exponential 2 theta s ds from 0 to t. So the result is actually sigma square over 2 theta times 1 minus exponential minus 2 theta t. And we can see that from when t goes to infinity, then this term basically will vanish, and then the expectation of xt will tend to mu. And also, when t goes to infinity, this term actually would vanish, and then the variance of xt actually will tend to sigma square over 2 theta. Okay, so this part. So we have actually solved this problem and see the properties. Okay, so actually the solution consists of 3 components: the long run mean, mu, and the deterministic decay to the mean, so which is this part. Okay, so x0, if x0 deviates from mu, then this deviation actually will decay with this exponential factor. And also we have this stochastic components, and the deterministic part actually shows how xt reverts to mu at the rate theta exponentially. So the stochastic integral represents the accumulated random shocks, and because the existence of this exponential decaying factor, actually the variance of these components has a limit.